All right, good afternoon, everybody. Welcome to the Firefighter Cancer Initiative monthly seminar series. Folks are trickling into the Zoom session, so we'll give about a minute or two for folks to jump in and get started. So just hang tight, settle into the webinar, and we'll get started in just a minute. And Tara, if you want to, oh, never mind, I'll do it. So for those of you that are just trickling in, you're joining us for the monthly Firefighter Cancer Seminar Series. We're just going to give another minute or two for folks to trickle into the seminar, and then we'll go ahead and get started. Again, just a repeat message. So you're at the Firefighter Cancer Seminar Series for the University of Miami. We're just giving another minute or two for folks to join into the session, and we will get started. Okay, so we're just about 3 minutes over, so we'll go ahead and get started in the interest of time. Welcome, good afternoon, or good morning, wherever you are joining us from, the other side of the United States or anywhere around the world. My name is Alberto Caban Martinez. I serve as the Deputy Director for the Firefighter Cancer Initiative here at the Sylvester Comprehensive Cancer Center of the University of Miami. You are joining us for our monthly Firefighter Cancer Seminar Series. We're close to the end of our 7th year of performance. You're in for a special treat today as we present our team from the Environmental Sampling Program, led by our own Dr. Sylvia Donner and Saf Nadeo. Today, we're joined by our trainees and staff who will be presenting to you to speak a little bit about this amazing program, which goes out to the field and samples the actual carcinogenic exposures that first responders experience as either part of their fire training exercises or in the field. So today we're joined by our team from the biochemistry department. So I'll turn it over to my colleague, Dr. Emre Dikici, who will start off first and then gradually introduce our presenters as we go along. If you have questions, there is a Q&A chat function along the side. My colleague, Tara Greenberg, will be monitoring them. And when we reach the end of our presentation, we'll be able to ask our presenters those questions. So please be sure to pop them in there. So without further ado, I turn it over to my colleague, Dr. Dikici. Emre? Umar, I think we may have lost Dr. Dikici. So should I turn it over to you or Alexa, should I turn it over to you?
I think I'll go ahead and start then.
Okay, thank you.
Yep. All right, so good afternoon, everyone. So my name is Umar Bakali. I'm speaking on behalf of the PI of the Environmental Sampling Program, Dr. Sylvia Downert, and I'm here along with my colleagues Alexia Kafkutsu and Shitvan Kilowala to talk a little bit about the Environmental Sampling Program, which is a facet of the Sylvester Firefighter Cancer Initiative. And our main goal is to sample firefighters and their occupational environment, determine chemical exposure and their health risks. So to get started, I have a little bit of an outline of the things I'd like to touch upon in the presentation today. a bit of our background of cancer in the fire service, and the significance of our work with the environmental exposure monitoring for firefighters. Passive sampling techniques, so my specialty for monitoring firefighter chemical exposures and applications to various firefighting contexts. And then I'll turn it over to Chitvan afterwards for his work on real-time sensors for monitoring volatile carcinogens in the active fire environment. And then finally, Alexia will present on biomonitoring methods with clinical samples for internalized chemical exposures and in vitro techniques for assessing the toxicity of aqueous film-forming foams. And lastly, our milestones and ongoing research. So a lot to talk about today. So without further ado, let's get into the background.
Umar,
Yes.
I apologize for interrupting you. So I know Dr. Donner was able to join us. I don't know if she wants to, before you go ahead and just start on that component, if she wants to say a word.
Okay, so thank you. Yeah, sorry for the mess. My link was not working, but really what I wanted to say was that really this is a team effort, and Umar introduced the speakers, but everybody else that is part of the team really have contributed a lot, including Alberto, Dr. Sapnadeo, Dr. Caban Martinez, Dr. Sapnadeo, Dr. Schaefer Sole, and Dr. Dikichi. And Umar explained, gave an outline or brief outline of what the talk is going to be today about. And just wanted to tell you that this is very much an evolving topic. Every time we have new research coming in, we adjust and we evolve and come up with new technologies, very exciting, that all serve the same purpose, which is to really contribute to, to help eradicate cancer in the fire service. So with that, I'm very thankful to everybody, and I let, including our firefighters and our team, because without them, we couldn't design these technologies without their feedback. So with that, I let Umar continue. Sorry for the interruption. But I really wanted to say that. And
yeah. Thank you, Dr. Donner. That's awesome. Okay, Umar, so we'll turn it back to you.
Thank you, Sylvia, and thank you, Alberto. All right, so let's get on with the background, cancer in the fire service. So the significance of our work for occupational and environmental exposure monitoring for firefighters. Okay. All right, so we know that firefighters have higher incidence rates for certain types of cancers compared to the general population due to the chemical exposure associated with their work. And there's lots of analysis that's been done in the literature, both chemical analyses, sampling, and meta-analyses, including work that's been done by our very own Dr. David J. Lee here at the University of Miami, which links the firefighter profession to elevated rates of cancers of the colon, prostate cancer, melanoma, testicular cancer, thyroid cancer, and so on and so forth. And the chronic chemical exposures are not only linked to these sorts of cancers, but also to cardiovascular diseases, respiratory diseases, and so on. So let's get into the implications of a firefighter's occupational exposure. So typically, a firefighter will be exposed to toxic compounds from an active fire scene or even a post-fire scene. This is where the smoke and soot and toxic gases are being generated. And that's where they can settle on the firefighter's turnout gear and personal protective equipment. So the personal protective equipment, therefore, becomes a vector for spreading contamination to other parts of the firefighter's work environment and even their own personal environment. So, for example, firefighters who ride with their turnout gear that's been contaminated inside the cab of a fire engine risk contaminating the inside of a fire engine where the others will sit. Or if they take the contaminated fire gear into the living quarters of a fire station, they risk contamination in there. Or even if they were to store their firefighter turnout gear inside their own personal vehicles or take it into their own personal home, they risk contamination to not only themselves, but potentially their friends and family as well. But of course, it's worth noting that a lot of protocol changes and policy changes have been put forth over the last few years to help prevent this sort of contamination. So definitely starting with on-scene decontamination to ensure that there's a reduced level of contamination. The green buckets, making sure to wash down with soap and water after an active fire scene has been controlled. The Clean Cab Initiative to make sure that firefighter turnout gear is stored in a separate compartment rather than inside the actual engine cab. to launder the firefighter gear and to make sure that it's not stored inside the living quarters of the fire station. These are all things that have helped reduce firefighters' exposure risks. So the environmental sampling program has mainly targeted polyaromatic hydrocarbons, although we aim to successfully analyze other analytes in the future. But we've targeted polyaromatic hydrocarbons as our main targets for assessing firefighters' exposure to carcinogens. So polyaromatic hydrocarbons are a class of known and suspected carcinogens by the International Agency for Research on Cancer that are produced during incomplete combustion. So fires that are fuel rich and oxygen poor, and they're burning a carbon-based fuel. So this could be anything between paper to wood to grease to gasoline to diesel. You have the potential to produce PAHs. And classically, combustion is when you take a carbon-containing fuel, you react it with oxygen, and thereafter it produces carbon dioxide and water. But when you have an oxygen poor situation, what ends up happening is that this fuel will start to react with itself under that very high temperature situation, producing aromatic compounds, or these ringed compounds, that are very stable at high heat. If we go further with that, these compounds will become larger, producing multi-ringed compounds or polyaromatic hydrocarbons. And further on, these compounds will coalesce and start to form particles. So the soot and smoke that you see from a fire, those are actually very, very large conglomerates of aromatic rings. And PAHs can hitch a ride on these particles. And so when the soot and smoke deposits on your turnout gear, the PAHs are coming with them. And that opens up the door to potential internalization. So there's different routes of pH exposure that can lead to internalization. There's inhalation, of course, which can result from inhaling smoke or soot at the fire scene when you're not protected by a respirator or a self-contained breathing apparatus, or even when you're doffing your contaminated turnout gear, you're not careful. If you haven't decontaminated and you eat or drink something, a little bit of that can get into your food or drink and you can ingest the PAHs. And lastly, if you have some direct skin contact with PAHs and you don't wash it off with soap and water in a timely manner, you can get dermal deposition of the PAHs that will absorb through your skin. So what happens after PAHs get taken up into your body or after internalization? So the body has a method for expelling foreign molecules in a process that's called xenobiotic metabolism. And in layman's terms, basically what this means is to take these PAHs, which are not very water soluble, they don't come out very well in the urine. Some of them do, but they don't come out very well, to make them hydrophilic, to make them water soluble. But in the process of doing that, the body converts them into very reactive species and generates increased reactive oxygen species as well. And this can lead to the formation of adducts and increased DNA damage, which leads to dysfunction in transcription and replication pathways, disrupting apoptotic pathways, and increasing inflammation, all of which can contribute to the onset of cancer. So let's move on to passive sampling techniques. This is my specialty. This is where the silicone wristbands come into the picture for monitoring firefighters' chemical exposures and applications to various firefighting contexts. So before we had started with silicone wristbands as passive samplers, we had done preliminary tests with particle counters and VOC detectors, and finding that in general, soot particle counts and VOC counts were very, very high at fire stations. So afterwards, we transitioned to silicone-based passive sampling tools since they've been shown to work well in environmental and occupational contexts as a collection device, a sampling device for volatile compounds in the air. And they're very ideal for monitoring carcinogens in the firefighting environment because they're simple to use, they're cost-effective, they're not invasive, they're easy to wear, and they can survive in the really harsh environments that a firefighter can work in. So preparing these silicone wristbands for passive sampling requires that we first solvent wash them to ensure that any extraneous contamination that didn't result from a firefighter's wearing them or from deployment in a fire situation, they're cleaned up. And then the solvents are then removed using a vacuum oven for a minimum of 16 hours. And that's to ensure that no solvents remain by the time that somebody wears them. And then afterwards, the wristbands are deployed to whatever sort of situation that they would be called in, whether it's a firefighter who's wearing them for a 24-hour shift, whether it's in a post-fire scene investigation, whether it's in an environmental monitoring context. And then afterwards, they're solvent extracted and then pre-concentrated for analysis using a method called gas chromatography mass spectrometry, or GCMS. And this gives us numbers to quantify firefighters' exposures to PAHs. So here's an example of one of the first things we did with wristbands in the context of looking for off-gassing firefighter turnout gear. So one way was to place these wristbands in a case containing sets of firefighter turnout gear that had been recently fire exposed, so within 72 hours of a fire, and then not recently fire exposed. And we found that there was a significantly greater amount of PAH exposure detected on silicone wristbands that were fire exposed recently. And this kind of sets up a precedent for the need for the green buckets for on-scene decontamination to ensure that less contamination is present on the firefighter turnout gear by the time it re-enters the fire station. We also found potential exposures within the fire stations themselves. So as you can see on the right, there's soot on the finger of a firefighter who rubbed down inside an ice maker. And granted, this ice maker was in a firefighter garage, but ideally you don't want soot with your soda. So wristbands that we distributed throughout the fire stations overall gave quite large readings for PAHs. And this sets up a precedent for informing firefighter leadership for improvements for safety protocols and improved filtration systems within stations as well to reduce the amount of PAH exposure. One of the other things that we looked at was a set of 72 structural firefighters, 47 of which who did not respond, to a fire call during a 24-hour shift, and 25 of which who did. And we found overall that 25 firefighters who did respond to a fire call within their 24-hour shift had larger gross PAH exposure on average compared to those who were not fire exposed within those 24 hours. But overall, both sets of firefighters still had greater PAH exposure than than non-firefighters. So every type of PAH, so every species of PAH has a part telling a story about where exactly the contamination is coming from. So whether it's coming from diesel exhaust, whether it's coming from grass, wood, and coal combustion. And so lots of authors in the literature have used in environmental sampling context ratios of different species of PAHs to conduct a forensic analysis of where exactly contamination is coming from. So for example, a ratio that compares fluoranthene to fluoranthene and pyrene, if that ratio is greater than 0.5, that's evidence of grass, wood, and coal combustion. So when we applied these ratios to our firefighters, the same set of 72 from earlier, we found that there was some interesting clustering going on. So we have here a comparison of different ratios, and each one of these fields corresponds to a different type of situation in which you would find the contamination. And we found overall that firefighters were exposed to some sort of combustion as their exposure source, but intriguingly, a lot of it was attributed to diesel combustion, which is a significant finding since we know that firefighters spend a lot of time around their fire engines, whether they're maintaining it, whether they're at the scene with them, even in the garage where the fire engines are stationed. We also recently conducted studies on fire investigators, and this is with Jeff Pauley up in North Carolina. So we distributed wristbands to fire investigators for a total of so far 35 different post-fire scene investigations. Each of these are individual post-fire scenes, so none of them are repeats, and none of them were the same fire scene investigated twice. And we found that on average, 90% of their exposure came from PAHs that were lower molecular weight PAHs. So that is to say, those PAHs that are more volatile at lower temperatures, at ambient temperatures that are more representative of a post-fire scene compared to an active fire scene. What we also found was that time spent at a post-fire scene positively correlated with exposure to PAHs. So the more time in general that a fire investigator spent at a post-fire scene, you would see generally a higher amount of PAH on the wristband that they wore. And then after we normalized by the amount of time that fire investigators spent at post-fire scenes, we found that younger post-fire scenes, so ones that were more recently extinguished, hot scenes, as called by the International Association of Arson Investigators, had significantly larger exposures to PAHs than those that were less recently extinguished or older fire scenes, warm and cold scenes. So we also took a look at location as a potential exposure source. So the overarching question was, what distance from a fire scene is safe? We know that in the fire services, the hot zone is considered the area with an immediate threat to life. That's where the fire is. Generally, like the burning building is the hot zone. The cold zone is the safe area where there's no threat from the fire. And the warm zone is the area of our main concern here, because this is where the staging operations take place. The PPE isn't always worn here. There's EMS operations happening here. There's a lot of busy work going on here. So we wanted to contribute evidence to establish some sort of guidelines for guiding what sort of carcinogen exposure would we see in the warm zone. And to do that, we distributed wristbands at distances from active fires in a controlled live fire training. So overall, we found that Class A live fires exhibited much more PAH contamination than Class B live fires. And this is understandably so, because Class A fires tend to produce a lot more smoke in general. So wood and hay and pallets that were burning in the Class A fires produce a lot more smoke than the more clean burning Class B fires, which were fueled with propane. What we found that was most striking, though, was that we can see a band here. And this is kind of a deposition front. It's a place where the pH exposure suddenly goes up before dropping off with distance. And this is thought to be because of the fact that when smoke and soot rises out of a fire situation, it goes up into the air. And then as it cools down, it'll start to crash out of the air and deposit a little bit of a distance away from the fire. And the real kicker is the fact that this deposition front coincides with the warm zone, where firefighters may not necessarily have their full personal protective equipment and SCBA masks on. And so this highlights the need for active analysis of volatile carcinogens in the warm zone and in active fire situations in general. And with that, I'll go ahead and pass it over to my colleague Chipan to talk about the development of real-time sensors for exactly this purpose.
Thank you, Umar. I will take it from here. Can you go to the next? As Umar discussed, there are several advantages of using silicone wristbands to analyze the exposure to firefighters. However, the analysis of this exposure has to be done in a lab using specialized equipment. So, yes. This means that there is a time delay between the exposure and the result. Additionally, a technical expert would be needed to analyze the data. A real-time system using sensors would provide immediate exposure levels and thereby allowing behavioral modifications to mitigate the carcinogenic exposure to the firefighters. But commercial gas sensors only target more acutely toxic compounds like hydrogen cyanide or carbon monoxide, which can lead to an immediate health concern. No current commercial sensors are available for chronic exposure to carcinogens, as is experienced by firefighters during their work cycle. These compound exposure over a long period of time has been shown to cause cancer. With that motivation, we started developing our own solid-state sensors to detect carcinogenic compounds. Solid-state sensors are able to respond quickly to the gas environment around them, making them ideal for real-time analysis. We developed portable electronics to detect the change in the sensor response and decided to deploy the sensors in real fire-like scenarios. Next. The sensors were initially deployed in a live fire training in Coconut Grove. Umar, next. The sensors were deployed right next to the burning fire for multiple reasons. It was important to see if the sensors and their respective electronics were able to work properly in such a challenging environment. We obtained some interesting results. We observed that the sensors were overwhelmed by the high exposure levels, leading to saturation of the sensors. The dips that you see in the first two graphs accurately correspond to the time points where the door was opened and the sensor was bombarded with a cloud of smoke from the fire. While the results were interesting, the positioning of the sensors was what firefighters would define as in the hot zone. At these locations, the personal protective equipment was mandatory for firefighters, and they were generally well equipped to deal with the exposure. Therefore, the environmental exposure at this location did not correspond to the exposures that the firefighter would get because of the protection from their gear. Therefore, it was decided to mobilize a sensor in the warm zone where the firefighters do their decontamination and are oftentimes without their personal protective equipment. Next. However, the warm zone is a large area, and as mentioned previously, the exposure is variable and depends on on multiple factors like the distance from the fire, the wind direction, and speed. Therefore, it was important to be able to place the sensor anywhere within the warm zone. To that effect, the sensor system was mounted on a teleoperated rover. This allowed for the sensors to be placed anywhere within the warm zone and also allowed it to move around within the warm zone. And therefore, they can be used by firefighters to scout exposure before making important decisions, and they're basing them on real-time exposure levels. We deployed the teleoperated solid-state sensor in Class B fires, similar to what you're seeing right now, as well as what you're seeing now, which is a Class A fire with flashover. As you can see from the video, the rover can be teleoperated to get quite close to the fire, and they can also be used to map the exposure within the warm zone. Next. The experiment conducted during the fire suggested a few interesting results. The most important results that we found was that the solid-state sensors were able to find exposure within the warm zone. The thing was that the location that the sensor was placed at had no obvious signs of fire, no smoke, no smell that could be visibly observed by a human observer. And the sensor still found exposure in these regions. Another important point was the amount of exposure. It can be seen from the graphs that the exposure is increasing over time. This is obvious to us as we talk about it because we see the fire, as fire keeps burning, the exposure just keeps ramping up. But it is an important component of going into a fire. The exposure that a firefighter would experience would not only be dependent on the fire intensity, the wind direction, ambient temperature, but also on how long the fire had been burning before the first responders got to the scene. This means that 5 minutes of firefighting different fires can lead to completely different amounts of chemical exposure. Therefore, it is very important to survey in real time the exposure in the field. Next. With that said, the end goal was not to add yet another complicated device for the firefighters to use, but to integrate the system seamlessly into their existing gear. To that end, the sensors were originally integrated into the emergency medical bags used by firefighters. Using design software, mechanical models were created, which were then printed in-house to create the sensor enclosing based on what the application required. For example, upon talking with our firefighter partners, they requested us to integrate the sensors into airtight Pelican cases, as they had switched to using Pelican cases for their firefighting. We therefore redesigned the system to fit within these Pelican cases so that we could test in real fire. Next. The goal is to make a portable system that can be deployed when needed and in the form needed for the given application for real-time carcinogen monitoring. The sensors could be integrated within a firefighter medical bags as shown previously for monitoring at the scene close to where the firefighters are likely to be present, or they could be mounted on a remotely operated rover to do real-time scanning of exposures around the fire and using it to scout to minimize the total exposure to the firefighters. Our aim was to provide the necessary information for firefighters to make the right decision. Next. We're currently working with our partners in the fire department to improve the sensor system even further. Using electrical design software, we have converted the current system into a stacked printed circuit board system. This allows for almost a 40 to 50% reduction in the footprint of the hardware, as you can see from the image on the left. In addition, the modifications in the electronics now allow for wireless transmission, which we are currently working on integrating. We have already transitioned to airtight Pelican cases from EMS bags to hold the sensor. And finally, we're improving the frequency of field testing and deployment using current and the new sensor systems. Next. This brings me to our latest deployment. We went to a live fire in Coral Springs last month on April 20th. The sensors were placed at the edge of the warm zone, very close to the cold zone where civilians like me can just walk through. The placement is marked by the red circle towards the right side of the image. The fire was taking place at the building in the back, the red building behind the fire trucks, where wood pellets and hay were used to fuel the fire. Additional smoke was generated with water vapor using damp cardboard throughout the building. We can see that the sensors were even further than the team of firefighters who have seen doing their decontamination. And we see from the results that despite the distance from the fire, there was a rise in sensor response, suggesting there is an increased exposure as time passes. Using this, we can safely say that using solid-state sensors to determine the amount of real-time exposure would greatly aid firefighters in protecting themselves from harm in the long term. I will now pass it over to Alexia, who will talk about how these compounds were found within the body.
Thank you, Chitvan. So in this next part of the presentation, I will talk about our methods for the assessment of the internalized carcinogen exposure. And next slide. In order to do this, it was necessary, first of all, to choose the right biomarker to assess the exposure. And there are various biomarkers in the literature, such as urinary PAH biomarkers, which include parent, that means unmetabolized PAHs in the urine, like benzoylpyrene, and the hydroxylated PAH metabolites, like 1-hydroxypyrene. And there are also biomarkers of PAH presence in tissues and peripheral blood cells, such as the formation of adducts between PAHs and biomolecules, like the DNA or proteins, or the presence of cytogenetic alterations that include structural chromosomal anomalies or the formation of micronuclei. In our studies, we are focusing on measuring parent PAH elimination in urine, because as a marker, it is directly associated to previous exposure, while it also integrates all routes of exposure. And another very important feature is its high specificity and the fact that it is less susceptible to intra-individual variability. Next slide, thank you. So the following slides will showcase our findings from different sampling groups, which were 21 new recruits from whom we collected urine at baseline and after certain live fire training exercises, 25 active firefighters from whom we collected urine before and after they went on a 24-hour shift, and we also had commercially available urine serve as our control. Now, the fire settings that the firefighters were exposed to were either Class A or Class B fires. And as you can see on the schematic, Class A fires are those that involve ordinary combustible materials like wood, plastic, paper, and Class B fires are the ones that generate from flammable liquids like petrol. And the gist of the protocol that we developed for sample analysis, it is similar to that of the wristbands that Umer described previously, though of course it has been tailored to the needs of having a clinical sample as matrix. And in a nutshell, as you can see, what we did was to apply pressurized solvent extraction in order to extract the PAHs from the urine, followed by sample cleanup and drying in order to fully remove any aqueous elements. And finally, we evaporated the samples and ran them through the GCMS in order to be able to qualitatively and quantitatively detect the PAHs. Thank you. So starting off with the 21 new recruits, in this cumulative heat map that you see on the right of the screen, we can see the total PAH exposure of the new recruits throughout the 4 different time points. So we have the baseline on the left, followed by Class A, Class B, and then Class B, where urine was collected after 18 hours. And it is very easy to visualize both in the heat map and in the dot plot on the left that the type of fire and the collection time can affect significantly the total levels of PAH exposure, with Class B fire being the one that had the highest concentrations. And our next group are the 25 active firefighters from whom we collected urine before and after they attended, as I said earlier, a 24-hour shift. And in this bar plot that you see, every bar corresponds to a different firefighter, and we see that their total exposure before and after the shift, so that would be the light green for the before shift exposure and the darker green for the after shift exposure. And we observed that there was a significant difference in the total levels of exposure before and after going on the shift. And the post-shift levels are quite obviously being much higher than the pre-shift ones. And this finding was corroborated by our survey data that we distributed to the participating firefighters. And truly, the ones that had the biggest increase in pH levels were also the ones who during their shift responded to actual fires. Thank you. So here we see how the exposure shapes based on the type of call that was answered. So on the left, you see the firefighters that attended the fire calls, while on the right, you see the firefighters who responded to non-fire related calls, such as emergency medical events. And it is evident that the firefighters who went to fire calls had a significant increase in total exposure, reaching very unsafe pH levels. In some cases, it is over 100 parts per billion. Now, looking at those who did not go to fire calls, we see that they exhibit mainly a decrease in pH levels, which was not significant, but it still remains much higher compared to our control population data and the CDC's anticipated total PAH exposure in the general population, which should be less than 5 to 10 parts per billion. And finally, next slide, please, Umar. Thank you. So finally, we looked at the number of fire calls that were answered by each firefighter. And this is visualized in the bubble plot that you see, where the y-axis represents the number of fire calls that were answered, and the x-axis represents the firefighters, each of whom has also been color-coded. And the size of the colored bubble represents the pH concentration. So obviously, the bigger the bubble, the more pHs that were detected in the urine that was collected after the end of the shift. And what we observed, as you can see, is that the highest concentrations can be found in firefighters who only responded to one fire-related event. And this shows that the number of fires is not the main factor that affects pH exposure. And we believe that this observation could be attributed to factors such as the duration or the magnitude of each individual fire, or potentially the types of materials that were burned, because we know all of these are parameters that determine which PAHs are released. And of course, not every PAH has the same burden. And at the same time, it is possible that throughout the shift, and by the time we collected the urine, some of the PAHs might have already been excreted or metabolized to other forms, or they might have already been bound to adipose tissue, which is something that happens due to the lipophilic nature of these molecules. So in order to address this, we plan in the future to collect urine at multiple time points that will allow us to better understand this phenomenon. And overall, our results suggest that the unsafe levels of PAH exposure that Umar and Chitvan observed in the occupational environment of firefighters, it also corresponds to the internalization of exposure as it is shown in the analysis of parent PAHs in firefighter urine. Next slide, please. Thank you. So in the following part, I will be discussing the main findings of a pilot study we performed within the FCI, where we assessed the toxicity of aqueous film-forming firefighting foams, or for short called AFFFs, in human kidney cells. So as you know, Umar, could I have the next slide? Thank you. So firefighters are exposed to parent polyfluoroalkyl substances, or else called PFAS, by using the AFFFs for Class B fire suppression. The thing is that since 2015, the production of AFFFs that contain highly toxic PFAS, like PFOA and PFOS, it has been banned because of the harmful effect that they may induce on humans, animals, and generally on the environment. Next slide, please. So one of the organs that seems to be highly affected by PFAS exposure are the kidneys. And studies have shown that having increased serum PFAS concentrations, it can lead to an elevated risk for kidney cancer. At the same time, studies on firefighters showed that they tend to have increased serum concentration of certain PFAS after attending training exercises. And what is even more alarming is the fact that firefighters have a higher risk for kidney cancer mortality compared to the US general population. So knowing how toxic the presence of PFAS is, the question we wanted to answer here in the study was whether the AFFFs that are currently being used in the fire service in two very large US fire departments, whether they exhibit similar toxicity or not. And let's not forget that in theory, all of the old AFFFs should have been phased out by now. So in order to answer this question, we incubated human kidney cells, as you can see, with 3 different AFFFs that are widely used, as I said, for Class B suppression. We added each of the foams separately in different concentrations that range from 0 to 100% stock concentration. So 0% is essentially a saline buffer. It is not harmful to the cells. And the 100% is the foam as it is in the bucket and diluted in the fire station. And then we performed several assays that allowed us both to visualize and to quantify cell health and the presence of toxicity. Now, being mindful of the time, I will only focus on our most major findings and highlight 3 concentrations of interest. So these are the 3%, which is the concentration that is used in the fire service for fire suppression, 0.3%, which is 10 times lower than what is used in the fire service, and as I mentioned before, the 0%, which is our negative control. Now, what we observed is that the cellular health was significantly affected at 3% concentration for all 3 foams that were tested. And you can see there was significant toxicity even at 0.3% concentration for foams A and B. And this can be visualized both on the bar graph on your left, but even more so in the fluorescence microscopy images on the right of the screen, where each healthy cell is colored in green. And where you see absence of color, this indicates dead cells. So ideally, if the foams were not toxic in the concentrations of interest, then we would get on each square an image that would be similar to the 0% concentration, where we see, plenty of healthy and happy little cells. But that is not the case. And the take-home message of the study that was recently published is that the foams that we examined, and which, as I mentioned before, they are very widely used for fire suppression, they still induce cytotoxic effect on kidney cells, which indicates that the switch to newer and safer foam formulations, it has yet to fully take place. Next slide. Thank you. So here I would like to summarize, I guess, the seminar by highlighting some of the ESP's greatest achievements as part of the FCI. First off, we have successfully developed techniques and protocols that allow us to evaluate the occupational environment of firefighters, such as passive sampling wristbands for chemical exposure assessment. We have also developed methods for the capture and analysis of volatile carcinogens in exhaled breath. As you saw, we utilized advanced solvent extraction methods that allow us to determine the internalized exposure in clinical samples like urine and swabs. And we have also developed, as Chitvan explained earlier, real-time sensors for monitoring chemical releases in fire scenes. And in our years within the FCI family, we have analyzed more than 500 samples from different firefighting groups that include structural firefighters, fire instructors, new recruits, as well as understudied groups that really deserve our attention, such as arson investigators, female firefighters, and wildland firefighters. And finally, we would like to highlight that some of the research that was presented here today has been published in environmental chemistry and occupational health journals, with more publications to come. And with that, I would like to thank, there is so many people involved in this effort, as Dr. Donert mentioned at the beginning of the presentation. And I would like to thank, we would all like to thank all the faculty, the scientists, and the students that are involved in the FCI, as well as all the firefighters, the unions, and the support groups that have participated in our research. and of course the state of Florida and the Sylvester Comprehensive Cancer Center for supporting this research. And of course, we owe a big thanks to all of you for attending today's seminar. And please feel free to hit us with any questions you might have about our research.
Hi, this is Sylvia Downer. Thank you, Alexia. I want to reiterate again, many thanks to our partners, the firefighters, partners in crime, because tailoring the technologies for their applications is very important, and without their feedback, we couldn't advance. And one thing that I want to acknowledge is the work of all the students that have worked through the years in these projects. And these projects are not trivial. They may sound, because you hear Umer and Situan and Alexia presenting in such a beautiful manner that seems like everything is seamless and it just happens, but it doesn't. It is very challenging research that these guys are performing. And I'm very proud of them as one of their mentors for all the work that they are doing. And it is hard research that takes so many hours to perform. And I really would like for all of you to understand that developing the technologies is tough, that each of those points that you see there involves a lot of work, and a lot of work that has to be done before to develop the methods, because all this is brand new. I mean, we are starting from zero and we are developing the technologies. So, a big thanks to everybody in the team.
Yeah, indeed. Thank you, Dr. Donner. It does take a village to do all this translational work, going from the bench out to the fire station. And we're incredibly proud of our biochemistry team, the environmental sampling program, and all these practices. We actually have a couple of different questions. So if you're curious and want to ask any of our presenters, I encourage you to go over to the question and answer box and pop it in. So we have a couple of different questions here, and I'll go ahead and get started. So Tara, if you'll help me clear the board as we go through them. Our first question is, there are clear differences between Class A and Class B fire PAH exposure levels. Some data shows higher PAH in A, while other data shows higher PAH in B. Was foam used to fight Class B fires that had lower PAHs? And would you expect large differences in cancer risk between Class A and Class B fires, mainly due to differences in the complex chemical mixture? So wow, that is a tough question. Who from our team would like to, Umer, this sounds like yours. I don't want to put you on the spot, but.
No, absolutely.
All right, go for it.
Okay, all right. So the first part of the question, yes, of course, there are very clear differences between Class A and Class B fire pH exposure levels. Generally, Class A fire pH exposure levels seem to be higher. And that's generally because there's greater levels of smoke and soot that comes out of a Class A fire. So one that's burning wood and pellets and bioorganic material, solid at that. I think this was in Alexia's work with the urine analysis. The Class B fires did appear to have a greater overall exposure to PAHs, at least internalized exposure. And sorry?
I only added certainly, please go ahead.
Oh, yeah, okay, yes. And I think the reason for that may just be because of differences in simply the type of PAHs that are being output. So Class A and Class B are very broad categories of fuels, and the type of fuel that was burning in Class B is not necessarily always the same. So propane might burn much more cleanly than something like a plastic backing, or or oil painting, or something like that's burning within a house that might also be considered Class B. Would I expect larger differences in cancer risk between Class A and Class B fires due to differences in complex chemical mixture? I don't think necessarily it boils down to just Class A and Class B, and just because there's a difference in the types of materials that comprise Class A and Class B. So there are some things that are definitely much more toxic in Class B than others that are more toxic in Class B. So for example, something like solvents that are burning might be much more toxic than propane. But treated wood in Class A might be much more toxic than just paper. So I think the differences are much more nuanced than just Class A and Class B there.
Indeed, thank you very much, Umar. So let's see here. So there's another question here from our live audience asking about, I guess, kidney creatinine levels or glomerular filtration rates and their exposure to PFAS and PFOA. Would the group have any comments or opinions on a way to early detect any type of kidney cancer?
So I'll take over this question. There is a lot of research out there connecting PFAS exposure with altered creatinine levels and the filtration rate. And it is even more eminent in people who already have developed chronic kidney disease. And it can lead to a downward spiral from there. What would be a way to early detect any kidney cancer in relation, I suppose, to PFAS? I'm not sure I understand this question. If anyone has any input, like a general marker of kidney cancer is what our attendee is asking.
I think they're asking the relationship between, let's say, like kidney function, so maybe creatinine levels or the glomerular filtration rate of the kidney and its relationship to someone having PFAS and PFOA, sort of like the...
Yes, I answered that. I say that there is a direct relationship between the two. They are affected. The filtration rate is, since the PFAS are being filtered through the kidneys, the filtration rate is lower when someone has been exposed to PFAS, and it is even more pronounced in people that have already developed, from what I know, chronic kidney disease, and there is not sufficient tissue oxygenation and such.
Which, I may add that also perhaps infection, if someone has an infection with high levels of creatinine, etc., and impaired kidney function, it should be screened.
Yeah, absolutely. And this is not clinical advice. This is just research advice for the purposes of our
Yes, absolutely.
But absolutely, Dr. Donner, that makes sense. We have another question here that from the audience. I think this one may be targeted to Umar. So we have an audience member that's curious about the wristbands. They want to know if there's an opportunity to get their hands on a couple of them and what would that process look like. And they appreciate sharing the information about the ice machines as that exposure is intriguing. So if you want to comment about the wristbands.
Well, definitely. We can definitely start a study. I imagine and mail out wristbands to have them analyzed. Just fair warning, there is quite a bit of a backlog of wristbands right now for analysis due to our other studies. So it might be a while before the results come back, but certainly we can definitely do something like that.
Okay, thank you, Umar. We have, I guess, one last question. So you sort of alluded and touched on this during the presentation, but just about what the sampling procedures look like for post-fire scene investigation. So when you have a fire investigator, and I know you touched about this in your slides, but anything you want to mention about the sampling process for post-scene auditing? Right.
So the intriguing part of post-fire scenes is the fact that it's not an active fire. So there's an allotted time where a fire investigator can start going into their investigation, and they can take off the wristband when they stop. And so that made it a little bit easier to record the amount of time that a fire investigator spent at a post-fire scene, and helped us with putting together the chart that correlated the amount of time that a fire investigator spent versus their PAH exposure. And we definitely plan on publishing this soon.
I also wanted to mention, so our colleagues from NIOSH is here, Todd, and he, NIOSH is currently working on the issue of going back to Alexia about kidney cancer markers with PFAS. So stay tuned, because there will be more information coming from our colleagues at NIOSH on that. So we have time maybe just for one or two more questions. This one is from an anonymous attendee that asked, were the wristbands worn under the gear, on bare skin, or over the PPE?
So generally, the objective here is to see what sort of contamination will permeate through the PPE to kind of get a feel for what exactly is the firefighter being exposed to that isn't being that their PPE isn't protecting them against. So the wristbands were generally worn under the gear on the bare skin.
Okay, awesome. And then I think, let's see, one last one. Could you recommend the use of any sampling and testing technology that focuses more on diesel exhaust exposure inside the fire station? If so, what would be the best way to follow up with someone for that information? So Chevan, I think this may be sensors for testing diesel exhaust or?
So yeah, we're currently, the sensors themselves are targeted at detecting PAHs overall. Sensors themselves cannot distinguish between whether they're from diesel exhaust or not, but they can do real-time sensing of these PAH exposures from any source. As for the best way to follow up, I'm currently designing the sensor to be real-time in the sense that you'll be able to see it. I need to build up a little bit more this thing so that it may be more palatable to non-scientists, essentially is what I'm trying to say. So I'm currently designing that, and we'll give an update on that when we're done.
Okay, awesome. Thank you very much. So we're just out of time. Again, I want to thank our biochemistry team under the leadership of Dr. Sylvia Donner and Dr. Deo, and all of our trainees. This is awesome work, and I know our firefighters appreciate everything that you're doing to try to do this early detection and, of carcinogens in the fire station. Today's presentation will be made available on the Firefighter Cancer Initiative website, so you'll be able to access that there for now. This is a reminder that our last cancer seminar series will be next month. Same time, same channel here. You'll receive an email from our firefighter study at miami.edu email address. Thank you all again very much. Again to Dr. Donner and the team for a terrific presentation, and we're wishing you a great week. Take care.
Thank you. Thank you
all.
all.
Bye, everyone.
Thank you. Bye.